Hey everyone, my name is Charlie Como, and this is my video lab report for the 5th lab, where I'll be modeling a collision between a Rubik's Cube and a tennis ball using the conservational momentum principle from Newton's third law and kinematics formulas derived from Newton's second law. I'll be using the software's Tracker to extract the data and VPython GlowScript to create a computational model of its motion. And we are interested in these results because if we do it right, we can use our models created here to model many other types of collisions such as car accidents, billiard balls, and molecular collisions. To begin with, we will need to make a few simplifying assumptions. We will assume a perfect transfer momentum between the ball and the cube, where the ball's velocity becomes 0 after impact with the cube, and the cube absorbs all the momentum from the ball. We will then assume a perfect hit, where the cube moves only to the left after impact and does not spin due to the angle of the collision. We will also assume that the ball rolls with no friction, that the friction acting on the cube is a constant force, and we will assume both the ball and the cube move in only the x direction with no y nor z components. Here's the actual video of the collision. With these assumptions, we can use the conservational momentum to mathematically derive the expected speed of the cube after the collision, with their two time steps shown pictorially here. Note the conservational momentum principle itself can be derived from Newton's third law. And then after the collision, the ball completely stops and the cube continues to move with the friction force slowing its motion and eventually causing it to stop. Using the velocity update and kinematics formulas derived from Newton's second law, we can calculate the friction force using the cube's initial velocity and total displacement as measured in Tracker. From Tracker, we can get the position data of the tennis ball and cube and calculate our tennis ball velocity and cube displacement like so. With these values and mass values taken from the internet, we can begin to fill in our conservational momentum and kinematics equations set up previously like so. With our assumptions, our model further asserts that the initial speed of the cube is 0.41 meters per second moving to the left. The friction force is 1.85 newtons to the right, and the coefficient of kinetic friction between the cube and the table is 1.431. Now we have all the data we need to set up our computational model in VPython. Again, our object's masses are taken from a quick Google search, and the initial object positions and velocities are all either derived or from Tracker. We have two while loops in motion, the first one being just the tennis ball in motion before the collision, and the second one being just the cube in motion with the friction force acting on it, and its velocities and position data calculated accordingly with the velocity and position update formulas. The time conditions are set to mimic Tracker, where the cube stops moving after 0.44 seconds. This is what it looks like when I run it. No, I also printed out the velocity of the cube, and at the expected time stop at 0.4 seconds, the cube model is still moving at a speed of 0.445 meters per second to the left. Letting the while loop run until the cube's model velocity is 0 shows that the cube comes to a full stop after 0.52 seconds, which is a 0.12 second difference between our predicted and actual results. And I believe the causes of these differences lies in my assumptions. From the video, it is clear that some momentum still stays with the tennis ball after the collision, and some energy is manifested as vibrations in both the cube and the tennis ball, and not represented as kinetic energy. Additionally, the collision angle of the two objects is not perfect, as some of the cube's momentum is transferred as angular momentum to make the cube spin, so as a result, the cube's true initial velocity is lower than predicted, which allows the friction force to stop the cube's motion in a faster manner. Some ways I can improve this experiment to reduce this error would be to use two billiard balls instead to eliminate the object spinning due to the angle of the collision, and to reduce the amount of energy lost to impact vibrations because the billiard ball will deform less. Additionally, I could also conduct a helper experiment to experimentally determine the coefficient of kinetic friction between the object and surface instead of just using large assumptions to theoretically calculate them. Overall, I was pretty happy with my experiment, and I'm very excited that this is the last lab for the semester. Thank you.